or it's going to be too late. You don't have to wait until the lab starts in order to learn Keysight Advanced Design System. You should start learning it now. All the materials to help you with the software already available on VLE. If you go, I think, log in VLE, learning resources, you're going to see the software package, no, not the software package, but materials helping you to work with the software. And of course, you are perfectly allowed to download and install the software with student license. Okay, I put the links in there already. You just click on the link that I put there, and then it will lead you to the place that you can download the software. And then you can activate it, I think, with your student ID or whatever would work. I have to inform you this. I'm not working for Keysight. Okay, I'm not their service. I'm not working in their service department. So whatever issues with the software, the first contact point is Keysight service. You send them an email. Okay, normally they're quite quick. They normally reply in 24 hours or a little bit longer, but normally they're quite quick. Okay, so in order to save your time, I would suggest you to download the software and install it right now. Okay, if something happens, so you can contact them on time, and the issues will be solved. Don't forget, you are not the only one who will have to use this software. This software is worldwide, so it's going to be a lot of people contacting them, even though they try to reply you within 24 or 48 hours, but still, you never know. All right, and the technical knowledge or the background knowledge of the software for me is zero, which means I know how to use it, but I don't know how the issues licenses or how the diagnosis errors from installation. So if that happens to you, okay, if that happens to you, please contact Keysight Service Department. Okay, but of course, during the lab work, if you try to design something, if you don't know how to use it, of course you can ask us. That we will teach you how, or we will help you. We don't teach you, but we will help you how to solve problem. But of course, you don't ask, okay, I want to design this, what to start? I will say, okay, good questions. Please refer to the learning materials, because you have a lot of materials there. For example, video streaming, you can start from very basic knowledge. Okay, you can watch a video there, and then they will tell you exactly what to do. And then we also have a PDF document file there, a very short summary, like something like 10 pages, to show you where to click to start and doing work. Okay, but of course, if you don't start working on it soon, then you will find yourself in the position that during the lab, you don't know where to start and you waste a lot of time there. Don't forget, for the lab, we have only 2 hours. Okay, and I wish everyone could finish all the assignment within that 2 hours and go home, get drunk, whatever afterwards. Don't have to care about the lab, apart from writing and summarizing your results. Okay, start working on the software package right now. Start working on the case study right now. Yes, please.
Actually, they will support with the license, free license?
The license, you have the student license, yes. Yes. We have an agreement with Keysight. So all of you will have a valid student license. Okay, all of you will have a valid student license. I don't encourage you to use special license that you might find from the internet. Okay, and if you do so, please keep quiet. Don't tell me a word. All right, we take it seriously at the school, because if you use that, on your personal computer, fine. If you're being caught, that is your problem, because it's your personal computer. But never install special private version on the university cluster. Is that clear? So we take this copyright seriously. Alright, now last time we just finished very basic introduction of the module. Yeah. So this is actually a one-page summary for the whole module actually. Yeah. If you know this, then you will pass the whole module. But of course, it sounds nice in theory. In practical, if you go in detail in each block, you will find it so complicated because there are a lot of things to learn. Alright, but this is just a summary of the whole module that we have to learn. What we have, we can summarize it into 3 sections. The first one is the transmitter. You will see the block, the schematic diagram there. We're going to talk about it soon. So the first, we're going to talk about the transmitter. Then we're going to talk about channel, the transmitting channel. Yeah, and then at the end of the day, it's going to be a receiver. So what you're going to learn, there's no more than these 3 things: transmitter, receiver, and a radiating and a communicating channel.
That's the whole communication.
Yeah, exactly. Seems nice in theory, only 3 things. But if you go, as I said, if you go into details, it's a lot of things to learn. For example, you see from the transmitter side, yeah, we start with the baseband signal. That's one module already. Signal processing, digital signal processing. We don't go in detail for that, but we're going to talk about it. A little bit about it. Yeah, we have baseband filter for filtering of the wanted signal or unwanted signal, or even signal shaping. Yeah, in the baseband regime. I guess everyone knows what baseband is. Do I see a hand? Can you explain what baseband is? What's the baseband signal?
That's the signal orchestrated almost centered on the 0. Oh.
Yeah, it's a raw signal. Yeah, it's a raw signal, pretty much raw signal. And normally,
It's not modulated signal.
yeah, it's unmodulated signal, it's a raw signal that we don't process anything, or we have it in the very low frequency. Yeah, for example, for speech signal, for baseband speech signal, it's from 0 to 4 kHz or something like that. Yeah, and then after that, we have a mixer. Now we start to shift the frequency from the baseband frequency or from low frequency to higher frequency. There will be a lot of things that we will discuss later in the next chapters why we want to shift the signals into higher frequencies. There are quite a few important reasons. Yeah? Among them, for example, you cannot communicate with many standards just in one single specific frequency. That makes sense? Yeah? 2G, 3G, 4G, and in the future 5G, they don't use the same frequency. They don't use exactly the same frequency. Because why? If you use 2G at 2 GHz, for example, you use 3G at 2 GHz, how can you discriminate the channels if you use exactly the same frequency? Even you use 3G frequencies, yeah? You use 3G frequencies, but in there you have the frequency slot between each user, and also sometimes time slot if it's going to be time multiplexing system. Okay? So we try to shift the frequency up, yeah, for some reason. One reason I just told you. The other reason is, don't forget, the antenna size is relative to the wavelength. Yeah, the highest signal frequency we have, the smaller antenna size you will get. So I can't imagine if you carry a mobile phone, an antenna is like this big. Yeah, your antenna, your mobile phone is like this big, and you have to carry it like that. So that's why sometimes we want to get to a higher frequency because we want to get small size antenna. And now you can see you cannot see your antennas any longer. Yeah, compared to the old generation mobile phone, it's like the big picnic pack. You carry there and you sit down, you call. Yeah. So this is why we need to have a mixer there, yeah, to mix from low frequency signal to high frequency. Yeah, in the mixer, of course, is composed of a multiplier and local oscillator. This is very basic one. We will learn the chip design, just mixer, local oscillator later. Yeah? And after that, of course, the signal passes through a lot of things already. So in the system, we have signal loss, then because it propagates through a lot of things. So that's why before we transmit it to the air, we have to amplify the signal. We have power amplifier over there. One lecture dedicated to power amplifier design. Yeah? And at the end of the day, you transmit it via the antenna. Okay? Basic system on the transmitting side, baseband processing, RF processing, antennas. Done. Three basic modules. But of course, if you go into details of each block, then you're going to find a lot of things in there. And then the modulated signal, I put it over there, FLO, F local oscillator, plus minus FM, this is the baseband signal. This is the modulated signal. It's sent through a wireless channel. Yeah? Sent through a wireless channel. We're going to discuss quite a lot about wireless channel, but we're not going to go like, I think you have the modules with Dr. McLennan, digital communication or wireless communication, something. Yeah, he talked a lot about channel, I guess, like Gaussian channel, additive wireless Gaussian noise channel. We're not going to talk about that. Okay, we're going to talk about channel modeling in reality. Yeah, how people model a channel, how they use this channel to predict the signal loss in the wireless channel. We're going to talk a little bit about that. And then after you send a signal through the wireless channel, of course, you don't send it for nothing. Yeah, you don't send it for nothing. You want someone to receive it. Yeah, or you want something to receive it. So that's why you need a receiver here to receive the modulated signal that you send from the transmitter side. And of course, it starts from there, not from here. So it starts from there. You have the modulated channel signal sent from the transmitter, received by an antenna. Yeah, received by an antenna. And then the first thing you do, because the signal travels from very far away, yeah, the signal level or the signal power level is going to be extremely low, I would say, in terms of minus 80-90 dB or minus 80-90 dBm, for example. So the signal strength is so weak. The first thing you have to do is to amplify that signal. Yeah? The first thing you have to do is to amplify that signal. So we have low noise amplifier here, but it's not just an amplifier. What you have is so-called low noise. It means this amplifier generates very low signal, very low noise power. And why? Don't forget, it's so weak already. Signal at the receiving antenna that is so weak already. If you have very high noise in the amplifier and you add the noise to the signal, there is a high possibility that you cannot recover the signal at all because the noise power is going to be dominating the whole band that you receive. So that's why the first amplifier has to be low noise. We will learn this much more in details when we talk about noise figure, noise factor. Yeah, we're going to talk about this, and you will see that this one plays the biggest role in the receiving side regarding noise figure that is contributes to the whole system. We talk about that later. All right, and then of course you do whatever to get the best signal quality out of it. So you see, this is like a reverse part. See? Now you demodulate the signal that you modulated from the transmitting side, and then you filter out some unwanted signal. We'll talk about this later to get the signal that you think is useful for you. And then of course, you amplify that signal again, and then you detect it. So you see the frequency go from low to high, yeah? And then it's reversed from high to too low again. So at the end of the receiver side is going to be again what kind of signal is it? The baseband signal. All right. So all these things we will learn in this module. We start with some terms that I think we should know, that we have to use in common. If you're from communications, if you have background in communications, I think you pretty much know all these already. Okay? But I have to remind all these again, so people from different backgrounds will understand exactly the same thing. So we start with decibel. Come from this guy, Alexander Graham Bell, who invented the telephone system. Yeah. And I can say that, okay, decibel or dB is a dimensionless number because this is a ratio of two power level. Simple so. Yeah. So we have, you see, the first definition is about the ratio of the power level. So what we can calculate is the power ratio in dB is 10 log 10 of P1 over P2 or P2 over P1. Doesn't matter. But you need to know what is the reference power and what is the power that you want to calculate in dB. Okay? If you want to calculate the dB of power but with the voltage, then it's not 10 log anymore, it's going to be 20 log. Yeah, don't forget power P equals V square over R. Yeah, and this square comes in the front, yeah, and times 10 there, that's why you get 20 log. Yeah, that's quite clear. And then if you want to convert back from dB to the power ratio or to linear scale, this is the equation you need to know. Yes, please.
No particular reason why P1 and P2 are switched around with dB and D1?
It's just the sign that will be different.
Oh. Yeah, but
The thing is that you don't have to remember this P1 or P2. What you need to know is that this is the power that you want to calculate into dB, and this is the reference power. So you calculate something in the reference of something. Yeah. I want you to understand. I don't want you to remember. That's what I mean.
yeah, but those two are opposites right now. If you had a P1 and P2,
That's fine. That's fine.
then
That's fine.
the numbers will be different.
Yeah. So I show you a table here. There are quite a few numbers that I think should be good to understand. For example, minus 3 dB, the power ratio is 0.5. It means 50% of the reference power. For example, you want to design a system. Yeah, you want to design a system, and we talk about 3 dB bandwidth or whatever. Then you know, okay, 3 dB bandwidth is the point where the power drops by, what is the percentage? I just said 50% from the, yeah, exactly, from the reference or from the maximum power. Okay? So, very useful to understand. Yeah? Again, here, minus 10 dB, minus 20 dB. You will find it sometimes unexplainable in microwave system because this field is extremely old. For example, with minus 10 and 20 dB, when you design a microwave system, then normally we have the rules of thumb that the signal reflection should be higher than minus 10 dB, which means maximum reflection, which is allowed. We're going to talk about this in detail. If you don't understand it right now, then it should be okay. So the maximum power, the maximum reflected power, which is allowed to design a microwave system, shouldn't be more than 10%. You know what I mean? So what we have a microwave system like this. Yeah, we have signal going in. We have signal coming out. Yeah, this is the input port. This is the output. Yeah, and if you know the term impedance mismatch. Yeah, impedance mismatch means that okay at the input, the device that you design and the output, they don't have exactly the same impedance. Then what happens? The signal here, part of it will go through. Yeah, part of it will go through. Another part will be reflected back to the terminal. Yeah, and this is what we are talking about. This reflected signal. So in general, when we design a system, we would want to limit this to, what is the percentage of it? 10%, which is minus 10 dB. And if you work in the lab, yeah, I don't mean in the 5333 lab, by the way. I mean in a research lab, like you are developing something totally new. No one has done this before. This requirement might go to minus 20 dB. 1% signal reflection is required, especially if you work for, I don't know, to design some military weapons or something like that. It needs to have very accurate results. Then sometimes this is the requirement that you need. Yeah, but for commercial or consuming product, then normally minus 10 for the signal reflection. Should be okay. And we have two sides here, positive side and negative side. Can you explain what really happens? Why it's negative, why it's positive? It's just say that the signal we want to calculate is bigger or smaller than the reference signal. Yeah? And why it's useful? Why it's useful? For example, you want to refer the output power to the input power, then you know whether your system is generating gain or loss. We're going to talk about the words gain or loss later. Okay, but I think most of you know what is gain and loss. Yeah. So that's why we need to know the sign as well. Yeah.
So you minus signs mean attenuation or kind of-
Yes. Yes. We're going to learn about this in a couple of minutes. Now we come to two very important words, gain and loss. Yeah. Very simple word to say. Gain is an increase in power level. How? For example, we have 1 milliwatt at the input. Yeah. You said an increase in power level, so at the output it should be more than 1 milliwatt. So if the power at the output is bigger than the input, then we call it a gain. Yeah, again. But of course, we're gonna learn much more in details in the later topic. Yeah, maximum available gain, effective gain, current gain, voltage gain, power gain when we design power amplifiers. So don't get confused. Okay, but now what we need to know, very basic term, gain. Gain happens when the power at the output bigger compared to the input. That's clear. Alright? So, and of course we just learned about dB, we have gain in dB as well. So, for example, if we have the power input of 1 milliwatt and the output power is 200 milliwatt, we said, okay, the gain ratio is the output power over the input power, so the gain ratio is 200. Okay? And of course, if the gain ratio of this amplifier is 200, once you change the input power, then you always know what the output power would be. I mean, in the basic term, but we will know that the gains will not be linear. It will be something else. But at the moment, we understand that everything is linear. Okay? And if you want to convert the gain in dB, yeah, then we have 10 log output power over input power, and in this case is 23 dB. Use the formula that we saw before. Okay? Loss, on the other hand, is the decrease in signal power. For example, at the output here, normally you get something smaller than whatever you put in at the input. Yeah, we call it loss. For example, in this system, we have P in, the input power, 1 milliwatt, P out, 0.5 milliwatt. So loss in ratio is input power, see, it's a reverse. Yeah? Input power over output power, loss in ratio is 2. So what you need to understand, you want to ask me something?
So this is an example you said before, like the -3.
It can be minus, so that's what he asked me before. It's just you need to understand what are you referring to. Okay? And I could say, okay, this is a gain of -3 dB as well. Can I say that? Yeah, I can say that. It's a gain of -3 dB, and that's there. It's well, but people don't say it's a loss of plus. Yeah, and people don't say it's a gain of minus. It doesn't sound sensible. But if you say loss 3 dB, it means that at the output you have signal power 50% less than the input. But you need to know which point you are referring to. So that's what you need to understand. So I don't want you to remember all these equations. You need to understand what exactly it is, and then you don't have to understand all this. Yeah, and as I said, sometimes it's called something like that, but I think it's not sensible to call something like loss of -3 dB or something. Yeah, I think it's loss of 3 dB. We know that it's a loss. Okay. So why we need to? There must be a reason. We already have something like power of 10 watt, 10 milliwatt. Why on earth we have to convert it in dB? Why make it so complicated to convert it? There are a few reasons. Okay, there are a few reasons. Because if you have the complicated system like this, you have the cascade of 3-4 amplifier with an attenuator. If we convert it in dB, it means we only have to plus or to add and to subtract it. But if you have the gain or loss in linear scale, then normally you have to multiply or divide it. Yeah, so it's easier to add and subtract it. So that's why we use dB. And the second thing is, it starts from, well, you know that the dB decibel comes from Alexander Graham Bell. So he invented, because it's come from the telephone system in the past.
It's not working.
We have voice signal. Yeah. Imagine about, is it loud? Is it a loud voice or not loud? Yeah. You have signal right down here. Yeah. It can be from 0 to 1,000 watt, for example. If you use linear scale, then all this small signal, will be neglected. But if you use log scale, like in dB, then this part will be amplified. Yeah, the range will be amplified. And the big signal, it's already big, it's very simple to detect. So it's going to be compressed a little bit. So it means all the signal strengths will be pretty much equally stressed. Yeah, if you use linear scale, then sometimes this part will be too small and you might not be able to consider it. That's why he invents this dB scale. You have to plot it like a log scale, so small part of the signal will be recognized. Okay? And of course, math operation will be easier because you have to add and subtract it. Yeah, this is just an example. This is just an example. You can see it by yourself. Anyway, I have to stress, even though this is an example, look very simple. Most of the time, it appears on the final exam. Not with this simple form, of course. I'm not a Santa Claus to give you out the marks. So not this simple form, of course. It's going to be more complicated, so it's your job. Yeah, start understanding this and expand your knowledge to more complicated system. Alright? So, what I have to say here then, if we have the linear scale or the ratio scale, what you have to do to calculate the total gain or the total output power over there, this is what you have to do to multiply and divide it. And unluckily, we never have this kind of very simple, like with gain 200, loss of 0.5. We have something like gain 23.345 or whatever, and loss of whatever, which is more complicated numbers. Yeah, so that's why it's a bit easier to use this dB form. And the idea is simple. You add all the gain and you subtract all the loss. Done. Yeah? Whatever you call it gain, you add it. Whatever you call it loss, you subtract it from the system. Then you get the final answer. Okay? Very simple so. Any questions before I go so far? I think it's still quite simple. And as I said, in communications can also used to express the values of the power. Yeah? Most reference power units are normally 1 milliwatt and 1 watt. If we refer the power level that we want to 1 milliwatt, we call it dBm. If we refer the power to 1 watt, we call dB watt. We use both. Yeah, we use both dBm and dB watt. But, normally, in wireless communication system, the transmit power is in the range of milliwatts. In the range of milliwatts. You don't want to have the phone next to your ear and it's radiate something about 1,000 watts just next to your head. No one's going to use it because you never know when it's going to explode. So normally transmit power is going to be something like 100 milliwatts, maximum 1 or 2 watts. So most of the time, or many times, not most of the time, many times you will see dBm, but also sometimes you will see dB watt. We use both, and many times you see dB watt and dBm at the same time, and it's your job to converse between these two. Okay, so if 1 milliwatt is used, we call it dBm, and then it's the same, 10 log power, yeah, in milliwatt, then you get dBm. So these are some numbers that I think we should pay a little bit more attention there, especially here. Here, 1 watt is 30 dBm, and I like it when I design my final exam. I mix everything. Yeah. You get transmitted power 1 dBm, and then you receive it with 20 dB watt, and then you amplify it with 20 dBm again, and get 2 dB watt out of it. What is the real gain? That's going to be your job. Yeah, this is what I like though. You see, you have power input, you have the gain there, yeah? And I told you already, if 1 watt is used, we call dB watt. And this kind of mixing units happen many times. We have dBm and dB watt in the same system because, I mean, this is easier for the designer. Something like if you are designing an amplifier, then it might be easier to have it in dB watts because the power level is high. You know what I mean? But if we are designing an attenuator, then I might use dBm because normally the power we're dealing with is quite low. So that's why people try to mix, and you cannot blame them because the person who designed a power amplifier must not have to be the same person who designed a filter. Okay? You can say, hey, I'm designing an amplifier, I will use this. If you don't want to use it, it's your problem. You know what I mean? So he put whatever parameters he thinks is convenient for him. It's your job to interpret what actually it is. Alright, and this is the basic things that I think you should understand. So, power in dBm is power in dB watt plus 30 and vice versa. I think that's the thing that you have to understand. But I think it's obvious because 1 watt is 1,000 milliwatt anyway. So you know that it has to be plus or minus by 30. I think that's quite simple to understand. Now we're gonna talk about return and insertion loss. Yeah. Believe it or not, you're gonna see this kind of picture throughout the lecture. You need to know what exactly it is. It's not a Christmas gift in there. Okay? What in there? It can be a component, it can be a device, or it can be a system. Yeah? What you have to know is it's not just a box. It can be a black box. You contain whatever in there, just an amplifier or the whole wireless communication, or it's just be a wireless channel like air, like this. Yeah? But you need to know it behaves something in there, and we need to understand that. So, we just discussed briefly, yeah, what happens when you have a microwave system. You have input port and you have output port. Yeah. What you have at the input is that, of course, you want to have a signal flowing in. Yeah. You have signal power going in, and then you have here something in there to process your signal. Yeah. Doesn't matter, amplify it, filter it, whatever. You need to know you have something in there to process your signal. At the output, you have some signal coming out. Can be bigger, can be smaller compared to the input signal. Doesn't matter, depending on this guy. Okay, that's the very basic microwave system. Actually, it's a basic electronic system or electrical system. In microwave system, we have a little bit more. Well, we have a little bit more. So, when you have input power going in, there are a few components of the power and a few paths for those power to flow to. As I said before, some part will go in there, yeah, get processed by this component and go out. However, if you don't design it in a better way, then some signal will be reflected. Yeah, depending on, of course, the system that you design. Yeah. So we call it a return loss first, easier to understand. A return loss when we have the ratio of the reflected power, yeah, and the power input. At the input, at the total input power is the ratio of the reflected power and the ratio and the input power. This is the thing. And then if you learn microwave system already, we have so-called S parameter. Did you study S parameter before? Scattering parameter? Your eyebrow look like question marks? Okay, it's gonna be complicated, it's gonna take a long time then. Because some of you have no idea what the S parameter is all about, and I think it's very important. I start again with the box. Like this, yeah? Also with, I would say, some signal going in, I would say V1 is a voltage. Make it easy. and something going out there. Yeah. Scattering parameters of a two-port network. Of a two-port network. I stress this. This is just basic S parameters. You can have three-port network, four-port network, and why it's called two-port network? Because two terminals are here. Terminal 1, I would say port 1. Terminal 2, I would say port 2. Okay? It's a matrix. Start to be more now. Yeah? So I will say its parameters like this is a matrix. Yeah? I will have port 1 here and port 1 there. Yeah? I say there are a few combinations that we can have here. We have the input here at port 1. Compared to that one, what we have is the reflected signal at port 1 and something transmit to port 2. We also do the same thing. We can have the input signal in this on this side as well. Yeah? If this component is not reciprocal, you know the word reciprocal? Yeah? It doesn't matter, you have the input at port 1 or port 2, the output will be exactly the same. And that's called reciprocal. You can put V2 and input here too. Yeah, input here too, and get something out from port 1. And also some reflected signal from port 2. Exactly the same thing, it's just you do it on both sides. Yeah, is that clear now? Until now? Clear? Yeah? So what we do in the microwave system is a bit more complicated than that. We say S11 is the ratio of, this is the incident, this is the reflected, yeah, is V1, not VI, V1 R over V1 in, with the condition that port 2 is terminated. And normally it's 50 ohm. Which means you don't care about the signal at port 2 now because it's terminated. You're not going to get the signal reflected and add to this. Okay, you're not going to have any disturbing signal coming from port 2. Is that clear in a simple word? So is reflected signal at port 1 over the incident signal at port 1 when you terminate port 2. It's called S11 or reflection coefficient. So it's reflection coefficient. Believe it or not, same equation, but it is already in dB. You can make it in dB too. 20 log. Yeah. Return loss is actually absolute value of S11. We call it return loss. You're going to use this definition quite a lot. Okay? And then I guess for S22, you can guess what happened. Can you tell me, please?
V2 reflected.
Yeah, V2 reflected at this port, yeah? Divided by incident V1 at this port. Exactly, but and port 1 is terminated by 50 ohm. Yeah? Exactly the same thing, it's just the other part. Now we come back to this. We're gonna come back to this again. I need to show you that they are related. Okay? So, and as I say, part of the signal will be reflected, yeah, from P in, and then part of it will go into this component, and in that component, it happens if it's not a lossless system. If it's not a lossless system, it happens that this component will either absorb the power, part of the power, or the power, I really don't know, depending on how you design it. This component will either absorb your power or dissipate the power. Okay? Simple so to make it understandable in the easiest way. If this is just a resistor, you put the power in there, part of it will be dissipated in heat. You lose some signal in there before you get something out at P1. You know what I mean? You are losing something there, which means if it's lossy system, you will never get, well, if it's lossy passive system, yeah, no external power injected into the component, yeah, then normally PT is smaller than Pin. We can divide it into two systems now, passive and active system. Passive system, you don't have external energy apart from the power signal that you put in there. It's like, for example, filter, yeah, something that absorbs energy. But if you have an active system, it means that apart from the signal power that goes in, you put an additional power in the system as well. Think about power amplifier. You need to have DC power going into amplify your AC signal. Is that right? Then we call that active system. And normally what we try to understand here is that normally if we have a passive system, then we lose energy. If we have the passive system, then PT is normally smaller than P1. But if we have an active system, then it's possible that PT can be bigger than P1. But we are talking now about the passive at the moment, okay? But active is going to be the same theory anyway. So the insertion loss is the ratio of the PT over Pin. Okay? If it's passive, then it means that PT is smaller than Pin. Yeah, if it's active, then PT is bigger than Pin. Yeah, and compared to this, we have S11, we have S22, which is only for port 1 and port 2 already. But we still have no link between port 1 and port 2. Is that correct? Yeah. So we have more definition. S21 is V2 or V out over V in. And you see, S21 is actually the gain or the insertion loss. See, they are related. Yeah? And on the other hand, we also have S12, which means now you use port 2 as an input and you use port 1 as the output. And as I said, if you have a reciprocal system, then normally S21 is equal to S12. And S11 also equals to S22. In the case we have reciprocal system. Is that clear? Yeah? Now you understand return loss, insertion loss, S parameters. Yeah? S11, S22, S21, S12. And normally you have to spend 3 hours learning S parameters in a lecture. Now I summarize it and I hope it's good as it is. If you want more details, then you feel free to go and read a textbook. But I guess this should be okay as it is now. More complicated system, we have phase transmission. I think we should take a break now. Yeah, in 5 minutes we'll take a break. I just want to finish this.